colleagues and I are undergraduate students at Colorado universities in the United States. And today we are very excited to present to you our investigation of shear capacity to facilitate more efficient short span UHPC beams. So some background on what UHPC is. It seems like a lot of you are familiar with the material, but in short, ultra-high performance concrete is a cementitious material with a compressive strength relatively 5 times greater than traditional concrete. Very impressive material. It contains short, randomly distributed steel fibers that is usually 1 to 3% of the volume of the specimen. It provides some tensile strength and it helps spalling and compression. And then the really unique thing about it is that it encourages multiple cracking within the specimen rather than one dominant crack forming like normal concrete normally would have. So in this figure below, you can see the crack progression that would happen in UHPC. So once cracks start to form, instead of that growing and becoming a more dominant crack, UHPC with the steel fibers, it facilitates smaller multiple cracks throughout the specimen, making it more durable, less permeable, and an overall more ductile material. And so some of the carbon impacts, this is a very fundamental arbitrary progression of how we made our UHPC more efficient. So as you can see on your left, this is just a normal cross section of ordinary concrete. And if you were to assume that UHPC has 2.5% more cement within the mix, but that its lifespan is 2 times longer than normal concrete, you can progress and make it more efficient. So from the first specimen to the next, we assumed the same reinforcement ratio, but instead of normal concrete, it's UHPC, and you can reduce the volume by 10%. Not a huge impact on the amount of cement you're using in your specimen, but it shows a little bit of reduction in size. But if you take advantage of the very high compressive strength of UHPC, Shear and Billing actually found that you can increase the reinforcement ratio to take full advantage of the high compressive strength and also the tension within the UHPC. So from the 10% reduction down to the even smaller cross section, you reduce the size of the UHPC by a lot, and that causes a reduction of 50% in cement. So that is very impressive. And then from our own previous research that we've done, we have even found that you can reduce the volume of fibers within the cement from 1 to 3%, which is typically used in industry, to 0.5% of steel fibers, and it still performs well under compression and tension, and still prevents spalling. So as you can see from this transition, you take a giant cross section of normal concrete, transition it with the efficiencies that we have found with our research and looking at lit review. You can make a UHPC specimen much smaller in size while still maintaining the same moment capacity. So it's a very impressive material, and this just shows how you can take advantage of the material properties and the lifespan of this material. And so our own research objectives is we really wanted to investigate the shear response of UHPC beams for efficient material use. So within our specimen, we assumed a 3.9 reinforcement ratio and 0.5% of volumes for all the specimen. We also wanted to examine the fiber alignment within our specimen using different placement methods. So as you can see on this, some of our specimen were casted from the ends, and then some of the specimen were casted from the middle, and to see the alignment of the fibers throughout the beam and if that has anything to do with its performance. And then we also changed 3 distinct variables, so casting method, transverse steel spacing, transverse grade, just to see the effects on the peak load, ultimate drift, and failure modes. And now my colleague Elizabeth Deco will be talking to you more about our experiment.
Good afternoon. So for our experiment, we cast 7 specimens of the UHPC. They were all short span specimens. You can see here on the left column the specimen names. You read them as such. On the first part, it'll be the placement method, mid or end. The second would be the transverse steel grade, and the final will be the transverse steel spacing. We use the United States Federal Highway Administration Code to determine our shear capacity and estimated failure mode for each of the 7 specimens. So the shear capacity is listed on the farthest right column, and all of our 7 specimens were expected to fail in crushing with a load of approximately 203 kilonewtons, but from our previous research, we determined that this would be extremely conservative. So these are going to be the cross sections of our 2 specimens, with the first 3 with the smaller transverse steel spacing on the top, and the 4 with the larger transverse steel spacing on the bottom. It's important to note here that our shear span to depth ratio was 2 for the entire, all 7 specimens. And then after curing, we conducted a 3-point loading test for all 7 specimens, with the results shown here. An interesting thing to note would be the one that's outlined here in red. The failure mode was shear for this one, even though all of them were expected to fail in crushing. And by comparing the peak load from experimental results and the shear capacity that we'd estimated, we find that these values were 12 to 17% conservative. And under the same assessment for the ones that failed in crushing, we find that specimens that failed in crushing were 34 to 51% more conservative than our estimations. And then now I'm going to pass it on to my colleague Josh Cates from Colorado State University.
All right, so we already had some great conversation about fiber orientation, and I'm going to add to that a little bit. So after we finished crushing our beams, we tested them until failure, and then we made 3 cuts. We divided each specimen into even quarters. So we're looking at this cross section. So for reference, this longer portion, that's about 77 centimeters. This cross section is about 10 centimeters by 18 centimeters, right? So we have this idea of aspect ratio that was previously developed. And really what that is if you imagine the screen is that smaller plane, that transverse plane, the steel fibers, how are they oriented? So they're gonna make an ellipse or a circle with that cross section. So if you think about it, you got the steel fibers sticking out like this. So if it's a perfect circle, it means that that fiber is completely perpendicular to that plane. And aspect ratio is the major axis of that ellipse divided by the minor axis. So the smallest that's ever going to be is 1, because if you think about it, the major axis is always going to be larger. The denominator is never going to be the larger number of that fraction. The very smallest it can be is 1 when you have both numbers being exactly the same values. So what happened with that? Well, we found that with pouring in the middle, so pouring at location B, we had the smallest value of that aspect ratio. So what that means is that that major axis was 1.44 times as long as the minor axis. So at B, we had specimens, fibers that were more perpendicular to that transverse plane than at the ends. So what happened when we poured from the ends? Well, exactly the opposite, which would make sense. So we had where we poured at A and C, we found that those fibers were more perpendicular to that cross section than it was at B. And that is the opposite of what we expected. Previous research had shown that fiber orientation had to do with flow of the UHPC, but we actually found, based on that image analysis with the aspect ratio, we found the opposite. We found that where we poured was more perpendicular, and where we didn't pour was less perpendicular to that transverse plane. So you'll find the exact same results when you pour at the end. You have, we thought that it was going to be less perpendicular where we poured, but we found that where we poured is more perpendicular to that transverse plane than where we didn't. And with that, I'm going to hand it over to my colleague, Darcy Farrow.
Hi, good afternoon, everyone. I'm the last presenter, and I'll be talking about the graphs that we created. Some important things to note, the two curves that you see are actually averages of all of our specimens together. And we calculated drift by the maximum displacement that we had in our beams divided by the shear span. And you can see there's not a huge difference between our mid-cast and end-cast specimens. They both reach approximately 275 kilonewtons. This is our transverse steel grade comparison. We varied between grade 100 and grade 40. We had 3 grade 100 and 4 grade 40 specimens, and all of the grade 100s failed in some sort of shear capacity. Also, not a huge difference in the peak load or drift. And we decided that some extra force could be developed by grade 100, but wasn't because we had a development length. We did not use hooked end fibers. We used, hooked end transverse steel. We used straight transverse steel. So we probably could have reached a little bit more of a carrying capacity if we had hooked our transverse steel. Okay, and then our last variable was the 0.5D versus 0.3D. We had 4 0.5D and 3 0.3D specimens. And there's a slight variation here. We had our 0.3D specimens had about a 24% increase in drift. And then the 0.3 specimens also had a better post-peak load carrying capacity, and that's that orange graph. Okay, so some conclusions. We expected our failure mode to be crushing, but a lot of our actual failure modes vary between crushing and shear, and a combination of both. We think that we know that the peak strength achieved from the specimens was exceeded from the code that we used, the Federal Highway Administration code. But the peak strength didn't significantly change with any variables, and the differences in fiber orientation were noticed with placement method, but did not actually affect any kind of specimen performance. And beams with closer stirrup spacing achieved higher ultimate drift and greater post-peak load carrying capacity. Some next steps, we'd like to expand our investigation of stirrup spacing to flexurally dominant beams, as well as investigate reducing fiber volume on durability and permeability. And I think some of what we're going to hear also this afternoon has to do with our last two next steps, which are responses to cyclic loading and irregularly shaped beams and pre-stressed specimens. Here are our references, and we'd love to take any questions.
Well, thank you very much for the nice presentation. Are there any questions? Okay, please.
Thank you for the presentation, and congratulations for all of you, because it's not easy to present to all about your work, and because you are still a master student, if I understood well. So I worked on shear and also on fiber orientation. My first question is, fiber orientation depends from workability of concrete, flowability, wall effect, and so on. The first question is, which was the workability of your concrete?
Are you talking about application, or how tough was it to?
Just the flowability of the concrete.
Oh, yeah.
If you did some slump test or something like that, just to know if it is very flowable concrete or.
Yeah, so the flow was very tough to work with, and we also, so these specimens were so small. Like I said, we were looking at a beam that was 77 by 10 by 18 centimeters. So our stirrup spacing, that transverse reinforcement, the space between that and where we were casting was so small. We think if we had a larger beam, there would be better flow, and we may see different results.
Okay, only suggestion, it's good to know, at least to have an idea about the workability in order to have the comparison of your results to the result present in literature, because we need to know how workable is concrete in order to see the flow effect, how it works in combination with wall effect, compacting system, and so on. And the other question I was to ask you, why did you study short beam, beam in which strut and tie method occur instead of slender beam in which steel fiber can significantly increase the shear behavior of the structure?
So part of it, we're an undergrad, like only undergraduate facility, and so we're a little bit limited by what kind of testing setups we have. A longer beam would be pretty difficult for us to even get the equipment to test those, so we kind of decided to limit it to mainly just short span beams.
Thank you. Congratulations again.
Other question? Yes, this is time just for last two questions.
Yeah, very good. Congrats on a very nice presentation. I wanted to ask you more about the exact methodology to measure the aspect ratio of fibers. So you use some sort of image processing, automatic analysis?
Yeah, so we used MATLAB.
Okay.
So what we did, so we imaged those cross sections, and then MATLAB converted those images to grayscale. And because we used light to image them, so the steel fibers being metallic, they're shining, they reflect that light, and the concrete doesn't. So when it converts to grayscale, all the concrete becomes black and all the steel fibers become white. MATLAB takes all of those white areas and draws an elliptical shape around it, automatically calculates that major axis divided by the minor axis, takes the average of all of those numbers, and then that's exactly what you saw when we have 1.59, 1.44. That's the average of every steel fiber that it sees in that grayscale image.
Okay, so very nice. Thank you.
There is another one, perhaps. Yeah. Okay.
Thank you for your presentation and congratulations on your work. I have a question regarding the fiber volume fraction. So you have chosen 0.5%, I think, for the steel fiber.
Mm-hmm.
And you also mentioned the reference from Shear and Wellington for choosing your reinforcement ratio about 3.9%. So was this low volume fraction intentional? Because in that reference I've read they selected the high reinforcement ratio to prevent the fracture of the reinforcement during the failure mode. So what was your reason for selecting a 0.5% volume fraction? Thank you.
Yeah, so this isn't our first experiment with UHPC. We've kind of been going at it for about 1.5 years now. And from our own previous research, before, I think the one right before this, we varied volume fiber fraction from 2% on the higher end, and we also did one with 0.5% just to see if higher volume fiber fraction does a lot more for its overall performance. And we noticed that it didn't really have a significant difference between its performance with the 2% versus the 0.5%. And for financial and equipment constraints, it was better for us in the end to use 0.5, and it still performed just as well. So it was based on previous research on why we choose the 0.5%.
And it's a little more sustainable.
Yeah, less steel.
Well, thank you very much. And that's the next one.